When you're rigging to move or support a conductor, there are other factors that you have to consider. For example, conductors are under various types of tension. 3 types of tension you should consider when rigging for a job are conductor or line tension, bisect tension, and guide tension. Let's begin with a look at line tension. Line tension is defined as the pulling force in pounds of a conductor pulling on a structure such as a dead-end pole. Let's look at this illustration to see one way of determining line tension. In this example, the conductor dead ends at pole number 1. One way to determine the approximate line tension is by using a formula. The formula reads tension equals conductor weight per foot times the span length squared divided by 8 times the sag in feet. We can see how the formula works by using some numbers from a job example. Let's say that the dead-end insulator on this pole has to be replaced. In order to plan the rigging for this job, the tension of the conductor pulling on the pole should be determined. Again, let's say that the conductor is 477 MCM ACSR. Well, we know from our earlier example that the conductor weighs 0.655 pounds per foot. In this illustration, the length of the span is 250 feet, and the sag is 48 inches, or 4 feet. Sag can be determined by using company charts or by using measuring instruments. The formula now reads tension equals 0.655 times 250 squared divided by 8 times 4 feet. Now, let's work through the formula. Let's start by squaring the span length. 250 squared equals 62,500. 0.655 times 62,500 equals 40,937.5. Below the line, 8 times 4 equals 32. The formula now reads line tension equals 40,937.5 divided by 32. The result, when rounded off, is 1,279. So the line tension pulling on the pole is approximately equal to 1,279 pounds. Now, an important point to remember is that the same tension exists throughout the entire length of a given conductor. So, line tension can be determined from any given span so long as the span length and sag are known. Rigging to safely lift or hold the tension of conductors on tangent or dead-end poles isn't the only rigging you'll need to do. For example, you may need to move or hold a conductor that exerts a force at an angle to other poles in a line. In these cases, you'll need to determine the conductor's bisect tension. Bisect tension can be defined as the pulling force of a conductor as it tends to pull a pole or structure into line with adjacent poles or structures. We can get a better idea of what's involved in determining bisect tension by using another illustration. This is an illustration of an angle or corner pole as seen from above. We'll label the corner pole P. The poles on either side of pole P are not shown to keep the illustration clear. This line represents a 477 MCM ACSR conductor. We'll label this span A and this span B. Span A and span B are both 250 feet long. One way to determine the approximate bisect tension is to begin by measuring a distance of 100 feet in line each way from the corner pole. 100 feet is a constant that has been worked out mathematically for determining bisect tension. We'll label the point 100 feet from the corner pole in span A, Q, and the point 100 feet from the corner pole in span B, R. Once these measurements are made, the distance between points Q and R is measured. That distance is 153 feet. Next, the distance of 153 feet is divided in half to determine the halfway point between Q and R. The halfway point is labeled T. The next step is to measure the distance between point T and the pole P. This line is called the bisect line. and it represents the direction of the bisect tension exerted on the pole by the conductor. In this example, the distance of the bisect line is 64 feet. At this point, the line tension of the conductor should be determined. As described earlier, this is done by working through the formula line tension equals conductor weight per foot times the span length squared divided by 8 times the sag in feet. The conductor weight per foot in this example is 0.655 pounds. The span length on either side of the corner pole is 250 feet, and the sag in each span is 6 feet. If the span lengths on either side of the pole were unequal, the sag in each span would also be unequal. Using the span length and sag from either span with the line tension formula yields the same result. Remember, line tension is the same throughout the length of a given conductor. After working through the formula, we find that the approximate line tension rounded off is 853 pounds. Once you know the line tension, the measured distances, and the length of the bisect line, you can find the bisect tension. This can be done by using the triangles formed by points P, Q, T, and points P, R, T. Let's start with triangle PQT. The tension per foot of line PQ can be found by dividing the line tension of line PQ, which is 853 pounds, by the measured distance of 100 feet. 853 divided by 100 equals 8.53. So there is 8.53 pounds per foot of tension on line PQ. Next, the line tension per foot, which is 8.53 pounds, is multiplied by the distance of the bisect line, PT, which is 64 feet. 8.53 times 64 equals 546 when rounded off. Now, because the triangles formed by PQT and PRT are identical, there are equal amounts of tension applied along the bisect line by the conductor in both spans. So the tension exerted along the bisect line must be multiplied by 2. 546 times 2 equals 1,092. Therefore, there is approximately 1,092 pounds of tension exerted by the conductor along the bisect line. In other words, there is 1,092 pounds of bisect tension trying to pull the pole into line with the adjacent poles. Now, there are a couple of other ways you can determine bisect tension. One is to work through this formula. Bisect tension equals line tension divided by 100 times the length of the bisect line times 2. The other way involves finding the approximate angle of the line at the corner pole and then using a rule of thumb chart to determine the approximate bisect tension. We'll take a look at how both of these methods work in the next part of the program. But before we do, make sure you read the text material for this part of the program.